That was a great intro, and thanks everyone for inviting me to join this this meeting. So I'm going to be talking about, excuse me, semantic chemical data modeling using LinkML. My name is Chris Mungall. I'm a researcher at Lawrence Berkeley National Laboratory. I also work on a number of the projects that you're going to hear about, such as the gene ontology. So I want to frame this just with a few stats just about the domain that I work in, which is more on the biomedical environmental side rather than the chemical side. So as we know, we've got a proliferation of like entities that we're trying to model, each involving complex data modeling. So millions, even billions of genes, proteins, substances in our different databases. But if you look at a registry like Fair Sharing, you'll see we've also got like 2,000 databases and 1,500 different standards for being able to manage all this information. So you might think we're doing a good job here of managing the complex data within this domain, and over 900 different ontologies with like 14 million different terms. So we might think we have this under control, but if you were to actually look at some of our databases, so just to pick on the INSDC sample database, which is capturing biomedical environmental samples for metagenomic sequencing, and they've got something like 10 million different entries. It normally conforms to one of these standards that are in Fair Sharing. But if you're actually trying to query the data and do some kind of meta-analysis where you look at how do different metagenome communities differ at different depths within the ocean, or at different levels of acidity, you'll see that most of these columns just are full of junk. The standards are not actually truly being applied here, and people just submit spreadsheets, and the spreadsheets just get loaded directly into databases without any validation. So we might think semantic web to the rescue here. The promise of the semantic web was through URIs and triples, the machines will automatically be able to comprehend data and humans, speech and writing and so on. So I think we've had some successes in the semantic universe. I would count the OBO project amongst these. So this is the only slide I've got on OBO. I'm involved with OBO. But I just wanted to highlight some of the work that we've done with providing a set of integrated ontologies like the gene ontology, the CHEMI, chemical entity ontology, providing both the sociological and the technical framework for allowing groups to collaborate, providing different tools for both being able to build ontologies and also to perform QC on them, ultimately allowing us to curate this vast universe of different genes and chemical entities out there. So I'm not actually going to talk much about OBO today, but I encourage you to check this out if you're interested in just exemplars of how an ontology community of practice could come together to model a particular domain. And also if you're interested in any of the tools we've either developed ourselves or that we've the tool list that we've curated to help you build ontologies. But I'm actually going to more go into the details of, okay, now that we've got these ontologies, how can we use them to actually help manage our data exchange? So let's say I need to exchange data with submit data to a particular database, maybe chemical sample data or something like that. There's perhaps hundreds of different parameters that could be captured. How well are we doing in providing rational and sane data standards for doing this? And what we tend to see is, or at least I tend to see in the areas I work in, is that we end up with a lot of siloization. We have people using nice semantic web tools over here, RDFL, Sparkle, Shackle Shapes, and so on. You've got developers who like to use Python and SQL databases, Mongo, the latest NoSQL databases, and also data scientists who maybe prefer more tabular representations, as well as domain scientists who like to just work with web portals and Excel. And so we often end up with this siloization amongst different tools. And so we developed LinkML, the linked data modeling language, as an approach to essentially provide a more unified modeling language that can be used to satisfy all of these different use cases. And so the basic idea is simple. You author your data models as simple YAML files, and these could be, complex, rich, relational style data models where you model interlinkages between genes and chemicals, samples, what have you. Or it could just be more like a data dictionary for being able to structure submissions to a different database. The idea is it's easy for both data scientists and curators to curate some of these models. And then our strategy is to compile down to other different frameworks. So you can translate these into OWL, you can translate them to RDF shaped languages like Shex and Shekel, to JSON-LD contexts, as well as more tooling that's more traditional and more recognizable to your average developer, such as JSON schema, Python data classes, and so on. And then you can essentially pick the right tools for the job. So you can use parts of the RDF infrastructure where it makes sense, and parts of more traditional infrastructures where that makes sense as well. So just to give you an example of I won't go into the language too much, but there's a lot of constructs that are probably quite familiar if you use something like UML or JSON schema or something like that. There's essentially, it's essentially an object-oriented style model where you have classes that can be related if you like, and then an inheritance hierarchy. Each of those classes have fields or attributes, and then you can compile these down into other frameworks. What it also allows you to do is model your instance data in the way that you would like. So it doesn't, just to echo what Burkhard was saying earlier, we maybe don't care so much about the underlying serialization as about the model itself, but we do want to make it easy for people who want to use JSON, who want to use RDF, who want to use TSVs and so on. So this example shows how you can create an object conforming to a LinkML class and just use the built-in loader and dumper framework to exchange data as JSON, as YAML, as RDF, or as TSV. We've got some ongoing conversations with a group called HDMF on HDF5 readers and writers. That's not quite there yet, but you can use this right now for either YAML or for any kind of RDF serialization as well. So one way this language goes beyond something like JSON schema is that it does support familiar constructs like enumerations, but it allows these enumerations to be backed by ontologies if you like. So all of the ontologization in LinkML is an optional layer that is nice to have that you can add on, but is not necessary. But what you can do is you can essentially declare prefixes in the block of your schema. We're actually working with Charlie to use kind of bioregistry as our main prefix registry, and then you can assign essentially meanings to each of the elements within your enumerations that are backed by different ontologies, and this gives you just an additional level of semantic rigor underpinning your data model. And because surprisingly to me, not everyone loves to author YAML files and manage those in GitHubs, we also provide a mechanism such that curators can author their schemas in spreadsheets using Google Sheets or Excel, and then have those essentially compile down to the YAML format, and from there onto some of the other formats as well. So I just want to give you a sense of some of the projects that are using this framework and that have been drivers in some of its development. So one is the National Cancer Institute Center for Cancer Data Harmonization, CCDH, where we needed to model certain kinds of core concepts such as specimens, research subjects, observations, and so on. And we needed to unite different kinds of terminologies and different ontologies, because with a complex domain like this, there's not going to be one ontology that rules them all. So this framework allows us to essentially define enumerations and use the appropriate ontology, whether it's the NPCI thesaurus, whether it's OBO ontologies like Uberon for anatomy, or clinical terminologies such as SNOMED. So one project I work on is the National Microbiome Data Collaborative. Here we're trying to provide standards for environmental sample data so being able to both characterize the environment, the biogeochemical measurements of those environments, and relate that to omics data from those samples. So we do metagenomic sequencing, but also metabolomics, proteomics on some of those data. And we essentially, we knew we needed to work in in a framework that could, could have essentially have scalable data management, because we knew we were going to have kind of like omics data in the terabytes, but at the same time we wanted to take advantage of semantic standards. So LinkML provided a good fit for this. So some of the core concepts here are things like studies, environmental samples, workflow analyses, data objects, and we leverage both OBO terminologies such as ENVO, the environment ontology, CABI for chemical entities, as well as more bespoke ones as well, such as GOLD, Genome Online's database environmental terminology. So one of the main drivers for LinkML was for building knowledge graphs. So as part of the NCATS, National Center for Advancing Translational Sciences project, we had a charge to create a schema that would unify a number of different groups building biological knowledge graphs. This is about 20 different sites. Only a handful of these were actually using RDF OWL, and we needed to essentially unify some of these knowledge graphs quickly, get everyone using the same terminology for node categories, for edge labels, and so on. So we used LinkML to build the BioLink model, including core concepts for chemical entities, genes, diseases, phenotypes, pathways, and so on. And then I just wanted to highlight a more experimental but recent project here called ChemROF, Chemical Entities, Mixtures, Reactions, Ontological Framework. And the idea here is to provide a data model for modeling the kinds of chemical entities that you may find in ontologies such as CABI, but to do this in a little bit more of a structured way, and to allow the conversion of data into ontologies. So the essential idea is to be able to kind of build up something like CABI using a more data-oriented approach. So just to summarize, I think experience has shown that authoring a lot of these standards and data models, people find this hard. We have these 1,500 different standards. They don't really interoperate very well together. They're not well adhered to. Adding semantics to these is harder, and it's expensive to have developers create custom UIs, custom validators for each one of these. So LinkML is designed to be an easy to use way to author some of these standards. It gives you a lot of the tooling, such as validators for free. And while it's built on RDF standards and the use of ontologies, it doesn't force these in your face. It allows you to gradually adopt them as you need them. And rather than working in competition with some of these other stacks, it allows you to leverage them where appropriate. So I just want to thank some of the many developers involved,